Yes, coming to the next part of our discussion. Last time we stopped at this point where we have written the heat balance between the absorber plate and the heat transfer between the fluid, which is the air, and also the heat balance equation for the bottom plate. So taking all these equations, we have simplified for the temperatures, and later we simplified for the heat transfer or the effective heat transfer coefficient equation. Now we are going to write for the useful heat gain equation. So finally we need to achieve the useful heat gain equation. So using those all substitutions in the earlier steps, from these steps we have substituted TBM, that is mean temperature at the bottom plate, TPM, it is the mean temperature at the absorber plate, and effective heat transfer, which is combination of the heat transfer coefficient between the fluid with absorber plate, that is H1, fluid and bottom plate, that is H2, and the radiative heat transfer coefficient, that is replacing the equation of radiation. Okay, the radiation equation, the part of the radiation equation is replaced by this HR. So that effective heat transfer coefficient we are writing in this way. So once we substitute all these values in the absorber plate equation, then we can write down as TPM minus TA, that is the difference between the mean temperature of the plate minus ambient temperature, like S plus S is the solar flux what is falling on the absorber plate. So S plus HE into TF minus TA. TF is the mean fluid temperature or the mean or the average air temperature. Then divided by UL is the overall loss coefficient, heat loss coefficient. It is at the top because here until now we have not considered the bottom losses. Then UL plus HE we can write here like this. Then taking the heat balance between the air, okay, heat balance between the air which is absorbing the heat and uh, from the bottom and the top plate. So if we consider the heat balance between the air and the plate, if you consider, I can rewrite these equations. That is, plate, we know the equation S equal to UL something, and we know for the plate mCp delta T equal to area. Area is, we have writing here, W into dx for the small section. W into dx you have taken. Some books also they have taken L1 and L2 also, width and length. Okay, and it is H1 TPM minus TF plus H2 into TBM minus TF. So in these equations, if you substitute these short forms of the different temperatures and heat transfer coefficient, one can finally write it as mCp divided by W into dTF by dx equal to S minus UL into TPM minus TA. So wherever in the above equation HE is there and TF minus TA is there. So if you substitute that HE value here, okay, and taking the equation of the heat balance of the air in this equation, again we have TPM minus TF. So this H1, H2, okay, if you take all these terms in one side, I can substitute HE as this term, HE as H1 plus HR into H2 divided by HR plus H2. So taking all those terms, one can note down after simplification, it is S minus UL into TPM minus TA. It is in the form of heat balance of the complete or the entire flat plate collector or the air heater. Now coming to the next simplification, that is taking this TPM minus TA. Okay, taking this TPM minus TA as S plus HE into TF minus TA divided by UL plus HE. If I substitute the entire equation for TPM minus TA. Okay, so later we can write it as on the right hand side, that is 1 divided by 1 plus UL by HE, because I am substituting TPM minus TA in terms of HE and S again. Okay, so that will be left with 1 by 1 plus UL by HE. Then inside bracket we will be left with S minus UL. Okay, S minus UL, TF minus TA. So this will be the equation after substituting TPM minus TA as this substitution. So S minus U will be as it is if you consider. Then inside bracket whatever terms you have taken, after taking this term with respect to S or uh, second term HE if you consider, we will be left with MCP delta T divided by W into dx equal to 1 divided by 1 plus UL by HE into bracket S minus UL into TF minus TA. Now here again you can recall the equations of the liquid flat plate collector, where generally we write equation as useful heat gain QU equal to F dash into S minus UL. This S is nothing but the solar radiation falling on the absorber with tau alpha. Okay, so that equation we have already written in the liquid flat plate collector, minus overall loss coefficient UL, that is the total loss coefficient UL, top bottom sides. But here we have considered only the top losses with different heat transfer effects. So I am writing here UL into bracket TF minus TA, because we have substituted TPM minus TA as TP, this entire equation. So it is left with TF minus TA. So why I am calling this as F dash, because already we know that the definition of F dash, that is the collector efficiency factor, as ratio of useful heat received by the absorber, is the ratio of useful heat received by the absorber to the useful or to the useful heat gain by the absorber, if the absorber plate is maintained at the fluid mean temperature. Okay, or the absorber plate itself is at fluid mean temperature, then I can call this term 1 by 1 plus UL by HE as F dash, or I can write it as 1 plus UL by HE raised to minus 1 as F dash, because inside bracket the temperature difference is with respect to mean fluid temperature and the ambient temperature. So I am recalling this as collector efficiency factor. Now whatever the left hand side terms are there, this is the useful heat gain by the liquid itself, mCp dt per unit area. Or I can take mCp delta T as the useful heat gain, F dash into area into S minus UL, TF minus TA will be the useful heat gain equation using this F dash or using the fluid mean temperature. So this we have seen already in the liquid flat bed collector. Similarly, coming to the other substitutions, okay, using the same equations, what I can write it as, I can separate now some terms in the right hand side, some terms in the left hand side, using the mean fluid temperature and the fluid inlet temperature. If I substitute, I can write it as S plus UL, sorry, S by UL, okay, S by UL plus TA minus TF. What they have done, they have taken S outside and UL outside. Okay, so once you take these outside things, then this minus term will be plus, that minus UL into TA. If you consider that minus UL into TA or minus UL into minus TA divided by UL will be how much? It will be TA plus TA. So that is considered here minus TF. That divided by TF. Now again taking the ratio with respect to fluid inlet temperature, same equation with fluid inlet temperature, then I can write it as S by UL plus TA minus TFI for the inlet fluid temperature. Once you consider that inlet fluid temperature, on the right hand side, we can write it as exponential of minus WF dash, you can see here, W dx into F dash. If I take it on right hand side, it will be W into dx or x after integration. Okay, after integration, you can take it as x for total length f dash into ul. So ul is multiplied from this equation. So that is ul whole divided by mcp, because here at the top it is mcp. Then what is the difference of temperature we are talking? Now after integration, this inlet fluid temperature is coming here. Okay, I hope you are getting the point. So to convert this entire equation for inlet temperature and the outlet temperature or the mean fluid temperature, one can take for the full length and for the full temperature difference. That is possible after taking the integration. So taking integration, I can write this in this form. Now this equation, I can consider it as whatever is there, like mcp divided by ul into area. Why area? Because it is w into x. So this I can call it as area. Okay, into bracket 1 minus exponential of minus f dash into ul into ap. That is nothing but f dash into area into ul divided by mcp. So this term can be recalled as fr. Okay, from the correlations, fr can be recalled again for the air heaters. That is nothing but the ratio of useful heat gain by the absorber to the useful heat gain when the plate temperature is maintained at the inlet fluid temperature. That is the definition of FR. Okay, so I can replace this term with FR, means I can again reform this equation taking MCP on the left side and remaining term on the right hand side. If I consider, then we can write QU equal to QU is MCP into delta T. Okay, so MCP delta T if I take on left hand side, and if I take all the remaining terms on the right hand side, considering this complete bracket with exponential terms, okay, as it is, I can write it as FR into AP into S minus UL is the loss coefficient into bracket TFI minus TA. Okay, so this we have found out for the useful heat gain if the heat removal factor is considered. What is that heat removal factor? Heat removal factor is given by this equation, as like in liquid flat bed collector. Now lastly, what we are doing here is this UL double dash is nothing but when same equation I have taken here also. Okay, better I'll remove this equation later. So here in the next step, for the general case, if you don't consider this UV, we can write in this form, where assuming this UL is only because of the top losses, not because of the side loss or the bottom loss. Because in the initial step, we have assumed without considering the bottom losses. Here, UV is considered earlier in the bottom plate heat balance. But later what we did, we assumed that bottom losses are very negligible or very less compared to the top losses. So if we neglect that UV, nowhere in the equations you can find the UV equation here. See, in the bottom plate, we have not written or we have not added the UV. But once you add that equation as UV, the bottom losses, without neglecting or not neglecting that form, because in the liquid flatbed collector, we have considered bottom losses, side losses, and the top losses. But here, what we are doing, we have neglected the bottom losses. Side losses are very negligible because the side, the entire side of the air heater, it is completely open for the air movement. It is not closed like flatbed collector or the liquid flatbed collector. So we forgot or we neglected to consider the side loss also. But side losses will be very less because air itself is moving in the sides of the flatbed collector. So later what they considered is, if we consider the small losses of bottom side, okay, so in that case we can write this UL double dash. So wherever this UL term was there earlier, it is just replaced with UL double dash. See the equations. FR in this FR equation, wherever UL term was there earlier, it is replaced with UL double dash. To consider the bottom losses also. One in the F dash equation. What they have replaced? QU can be written as QU or F dash. F dash is 1 plus UL dash by HE raised to minus 1 as it is. But in this form, if you write, okay, that will be useful heat gain QU equal to F dash into area of the plate into S minus UL double dash. So what is this UL double dash? This UL double dash denotes considering the bottom losses of the air heater. Okay, if you consider, one can write that UL dash is the top losses plus the bottom losses. So effectively, if you consider the bottom losses that they have shown, that is written as 1 by F dash, that is a collector efficiency factor 1 by F dash into UV into H2. Okay, bottom loss is taking place from the bottom surface of the bottom plate. So UV into H2 is considered here, divided by how the heat transfer is taking place. It is taking place by convection as well as radiation. So radiation effective heat transfer is taken here as HR. That HR is nothing but we have defined here in the earlier steps. In this, the HR we have taken. For what purpose? HR you have taken for the replacement of the radiative heat transfer. Okay, so radiative heat transfer, whatever is there, in this case, we have replaced with the effective or the equivalent convective heat transfer coefficient, that is HR. So here, what they have done? HR plus H2 plus UV. So this HR they have considered radiative losses top side or the bottom side, whatever. So keeping focus on the bottom side, they have considered radiation as well as convective heat losses at the bottom. So replacing this UL dash, okay, or UL dash in the other forms, like say for example in this HE also. HE is the effective heat transfer coefficient, considering the heat transfer coefficient between fluid to the absorber plate, fluid to the bottom plate, and the radiative heat transfer coefficient and the bottom loss coefficient. If you consider, I can write HE as like this. So finally, we are going to replace this UL dash by adding this term, this entire term, and we can write the useful heat gain by either two forms. One is the collector efficiency factor, another is the heat removal factor. Okay, here also you can just see the earlier equation, MCP delta T divided by area, or you can consider F dash into area. S minus UL double dash is taken here. Earlier it was just UL. In this F dash you can see S minus UL, TF minus TA. So here UL double dash is not considered earlier. That shows bottom loss is not considered. Okay. If in the problems, if they have given the bottom loss of the this loss coefficient with respect to top or the bottom both, if they have given, then no need to consider these equations. Directly you can substitute the values, you can get the useful heat gain or the factors, other factors. Then last term, what we left in this derivation is the flow factor. Flow factor is the ratio of FR by F dash. That is ratio of heat removal factor to the collector efficiency factor to find the flow factor. And the last part in this topic is using the Nusselt number, how to find the heat transfer coefficient. Because once you know the heat transfer coefficient, okay, so for finding the heat transfer coefficient or to know the other parameters, you can go for the Nusselt number. So generally we know the Nusselt number is heat transfer coefficient between the fluid and the surface, H. Then the characteristics length, that is L or D naught. So in this D naught is taken because considering if a tube is taken for the liquid platelet collector, you can take D naught. Or if it is a duct of air, one can consider this D naught as the effective cross section area or the characteristic length as D naught, not area. It is a characteristic length or the characteristic diameter divided by K. K is the thermal conductivity of the given material. So knowing this general formula, and for the given air heaters, there are many Nusselt numbers are there. But theoretically, if the Nusselt number is not mentioned in the problem, one can directly consider any of these equations. One correlation is using by case correlation, that is Nusselt number is given by 0.0158 Re raised to 0.8. One more Nusselt number equation is 0.0344 Re raised to 0.75 divided by 1 minus 1.586 Re raised to 0.125. So better, if you don't recall these equations, sometimes other Nusselt numbers will be given in the problem. Just we need to substitute the given values in this Re. So how Re is calculated? So Reynolds number, I think everyone knows how to calculate. So I think we have studied from third sem to this semester how to calculate the Reynolds number for any given flows, that is rho Vd by mu. Or here one can consider rho V the characteristic length or the effective diameter or the hydraulic diameter you can take for the pipes, that is rho Vd naught by mu. Mu is the viscosity of the given fluid. So once these values are known, one can find out the Reynolds number, and for the turbulent flow you can substitute in this Nusselt number. And many times for the liquid flat bed collector, the flow is maximum time it is laminar. Okay, and for the even with the liquid flat bed collector also we'll consider one problem here, just to understand the Nusselt number effect and how to find out the temperatures or the heat transfer coefficient, that also we consider. And here you can see for both Nusselt number equations, if you consider any one, the experimental values will be differing within the 10% error. So any equation, if it is giving within 10% error, you can go for that equation. So both equations can be considered. It is not like either we have to go for Malik equation or the Kay's equation. You can use the Kay's equation, which is simple one here, or with a different equation if it is there, it will be mentioned in the problem. Okay. So here they are telling for Reynolds number ranging from 10,000 to 20,000, the values are within 10%. Means it is only for the turbulent flow. If it is a laminar flow, then the Nusselt number can be taken from the heat transfer data handbook, or that Nusselt number correlation will be given in the problem. Okay, and for this air heaters, the solar air heaters, the duct characteristic length is given by approximately the characteristic length is given by 4 into cross-sectional area of the duct. So here cross-sectional area of the duct is finding is easy because it is having some height and width. That is the cross-sectional area. Then vectored perimeter. So perimeter is nothing but width plus height of the duct. So one can find out that perimeter. Area one can find out because it is a rectangular section. You can find out the product of width and height of the duct. So by that one can find out the characteristic length or the diameter, hydraulic diameter you can call. So that D naught one, once you find out, you can find out the Nusselt number, Reynolds number easily. Okay. Or if any other parameter is asked, like conductivity is asked, you can find out if heat transfer coefficient is required to find out, that also you can find out. Next is, so I am focusing on this because in the liquid flat bed collector we are not focused on the Nusselt number because it was laminar flow. We'll take one more example, whether the laminar or turbulent, if the Nusselt number is given, how to solve for that also. We'll take one example later. So here, now coming to the other factor, like say for example pressure drop. This is very important for the air collectors, not for the liquid flat bed collectors. In the air heaters, if the pressure drop is very high in the flow or if it is very less, so there what happens, the energy required to generate the hot air or the flow of the hot air to increase is very difficult. So it should be in between the high pressure drop or the less pressure drop. It should be minimum, not very less also. If the pressure drop is very less, then the flow is also not possible. If the pressure drop is very high, to generate the flow, we need to go for the pumping or we have to use the blowers. There's some external source of energy is required or the electrical energy is required. That itself is maybe more than the what the efficiency of the energy of the air heater is taken out. So better the pressure drop should be less so that any external pumping or blowing is not required. So for that purpose, we are finding this pressure drop. So that is found out by using this Blasius equation. So Blasius has given one pressure drop equation, that is dimensionless pressure drop equation for the smooth surface. So to find the roughness of the given surface, we are using this F factor, roughness of the surface. That is F is given by 0.079 Re raised to minus 0.25. That is given by Blasius. Then the pressure drop equation, now substituting this F, one can find out what is the pressure drop in the flow. That is considered as 4FL rho V square divided by 2 dE. It is almost similar to Darcy-Weisbach equation, what you have learned in the fluid mechanics subject. But there we have considered the friction loss. But here it is a pressure drop. So that is similar to the Darcy-Weisbach equation, that is 4FL V square by 2 GP. But here for the pressure drop, it is replaced with these terms. 4FL rho V square divided by 2 dE. So dE or d naught both are same. D is the effective diameter, d naught is the characteristic diameter. So you can either substitute d as d naught, or if it is given, you can substitute directly. So by this, one can find out how much is the pressure drop in the flow, then what is the Nusselt number or Reynolds number in the flow. So after finding this, one can understand how the heat is flowing between the air and plate. What is the time now? 8:29. Okay. So in this you can see, in the syllabus if you see for solar air heaters, it was about introduction, performance analysis that we just discussed. List the types. So types of air heaters, almost all the air heaters we have discussed. But in this, after listing, they have told about discussion on two-pass solar air heaters of conventional type. But in this PPT, I think we have discussed all the types. Okay. So we discussed UTC type, this PVC, plastic air heaters. We have discussed modified solar collector, all types maximum. So these are the two-pass. These are the two-pass air heater discussions. These are the simple type, simple air heaters with different passages. Okay. Or it is nothing but an introduction to air heaters, how air heaters are designed and how they work. Okay. Lastly, we'll take some simple example just to understand the performance analysis, because until now we discussed all these equations. Just to understand the importance of that, we'll take one simple problem with 2-3 steps. Okay. So here one question is given. So as it is not mentioned in the syllabus, but still to understand what is the performance by performance analysis, how we can find out some unknown terms in the solar air heaters or the liquid flat plate collectors. Both are in the similar fashion. So for that purpose, I have taken one problem. We'll solve in the class. Next problem you can take as a homework. So here for the air heater, they have given a flat plate solar collector 1 meter wide, okay, 1 meter wide and 3 meters long, is used for air heating purpose. So here whenever the flat plate solar collector is given with wide and long, this itself we are going to consider it as a channel of the air. Okay, because here they are not mentioned what is the complete side distances. So this becomes a complete channel of air, or it is a complete box. Okay, so how it is differentiated, we can see the question also. Air at 40 degrees centigrade and 1.01325 bar, atmospheric pressure. So the air temperature at inlet is 40 degrees centigrade. Maybe it is in a desert conditions. So that's why at atmospheric pressure, the air temperature is 40 degrees centigrade. Already the air is at high temperature, still we have to heat it. Is following through a collector with a velocity of 4 meters per second. So this air is moving at a velocity in the channel at 4 meters per second. Absorber plate and glass cover. Now they have mentioned it. If you have mentioned, you can take this. Otherwise, if you have not mentioned, you have to take this itself as a air channel. That 1 meter wide and 3 meter wide. But when you have given absorbable plate and glass cover distance, that becomes the air channel. Otherwise, you have to mention whether the air is passing through bottom plate and the absorber plate, or whether it is flowing between glass cover or the absorber plate. Now, in this air heater, the absorber plate and the glass cover are located at 5 centimeters apart. The solar heat flux falling on the collector is the definition here. Solar heat flux falling on the collector means it is falling on the glass cover. Then after glass cover, it will reach to the absorber plate. So once this concept comes, we can also find out this transmissivity and the absorptivity. Because after falling this much energy, 630 watt per meter square, okay, per unit area, 630 watt of solar energy is falling, but it is falling on the glass cover, then it is transferred to the absorber plate. So some energy is lost there because the glass plate is going to reflect and reflect some energy, and also it is going to absorb some energy. So these phenomena is called as transmissivity and the absorptivity phenomena. So using that, one can find out what is the actual heat flux falling on the absorber plate. So the absorber plate is very important. So finally, what we need to find out by using these all given data, we need to find out the temperature of the air coming out of the solar collector. Means the air at 40 degrees centigrade is the inlet temperature. Outlet temperature we need to find out. What else is given? Atmospheric pressure is given as it is. Total flat plate collector width is 1 meter. Length is 3 meters. So you can consider W as 1, length as 3 meters. Then velocity is given. Y velocity is given, we'll see. 4 meters per second. Then distance between, see here, the height of the air channel, because this is required for our Nusselt number, as I told you, the characteristic length of the hydraulic diameter, okay, or hydrodynamic diameter, if you see, or the vector diameter, if you see, that characteristic length of the height is 5 centimeters apart. The height of the given surface, where the air is moving or the fluid is moving. So now to find out temperature, so I think you can assume here when the air is moving between the plate or above the plate, the air is going to collect the heat or absorb the heat by the convection process. Okay. So if it is convection process or any other process, we know some formula, that is by the heat transfer subject, we can write it as heat gained by the any fluid. I can write it as Q equal to HA into delta T. Or if it is a conduction, I can write Ka into delta T. Or if it is radiation, I can go by the Stefan Boltzmann constant and epsilon of the emissivity of the given plates. But here epsilon is given or not, I don't know. So HA delta T or Ka delta T to see. So if it is a fluid, I can consider heat transfer coefficient H between fluid and the plate. Delta T I can consider it as inlet and outlet temperature difference. A is the cross section area. Okay, or sorry, surface area of the plate or the cross section area of the plate. How much it is in contact with the air. That area you can consider, and one can find out the H value if you know the Q value. So in that way, what I'm doing here, I am going to find out H value first, because we need to find the temperature. And to find H, as we discussed here, what is H? H can be mentioned in Nusselt number also. H equal to Nusselt number into K divided by D. How to find out D naught? 4 into cross-sectional area of the duct divided by wetted perimeter, or characteristic length also you can take directly. Then one can note down this H. Then how to find out this Nusselt number? Because here we need the Nusselt number. The Nusselt number here in the problem, 21. Assume tau of glass cover 0.85, absorption of the absorber plate of the glass cover, it is 0.9. So here tau alpha is given, that much loss we have to consider with S value. S is 630 into tau alpha will be losses. Use the following properties of air. So this is also given. Mu is given 2.07 into 10 raised to minus 5 kg per meter second. So where it is required now? If you recall this Nusselt number and other relations, to find the Nusselt number, we need Reynolds number. So for Reynolds number, we need this viscosity. Okay. So dynamic viscosity is required here, mu is given. Then also what we need, rho is required. Rho is nothing but the air. We now see here where velocity is required for the Reynolds number. D naught we need to find out. So like this, we are going into problem itself. So viscosity of the air between the plate and the moment, it is 2.07 into 10 to the minus 1 kg per meter second. Then Cp value is also given. The Cp value already we know from the liquid capillary filtration, mCp delta T. The mCp delta T may be required later. So they have given the specific heat of water also here, 1.005 kilojoules per kg degree centigrade. Prandtl number is also given, Pr equal to 0.698. Conductivity is also given, 0.03 watt per meter Kelvin. Here it is in Kelvin, this is in degree centigrade. So I can follow one of the temperature in the substitution paper. Now also in the problem they have given, use the following correlations. That is Nusselt number, you can use 1.86 Re into PR raised to 0.33 for laminar flow. Next is Nusselt number is 0.0196 Re raised to 0.8 PR raised to 0.3 for turbulent flow. This is a question. This entire thing is a question. I'm not telling this is important for our syllabus or syllabus is not mentioned why you are following. But you can understand many things by this problem. The importance of this sort of procedure to solve the problem with the solar air heater or the solar water heaters. So here they only is mentioning what Nusselt number can be used. They have mentioned and what Reynolds number of the Prandtl number can be used. That is also given in the problem. So Prandtl number is given here. Left is Reynolds number that we need to find. So finally, what I am doing now, I am considering the flat plate collector like this, absorber plate, the glass cover between that 5 centimeter duct is there. Below will be insulation. Total length, total width is 1 meters. Length perpendicular to the screen, if you see, that is the length of the collector. 3 meters is given. Now, coming to this finding Reynolds number. Reynolds number is given by rho Vd naught divided by mu. Rho Vd is what characteristic length is required here. V is velocity given in the problem. Rho is the density of air. Mu is viscosity given in the problem. So density, if you see, by ideal gas equation, density can be found out by rho equal to P by RT. Okay, I think this you can recall again here, or P equal to RT into rho of air. So by that one can find out the density of the given air. For that you can substitute the given values. 1.01325 bar it is. So we need to convert it in other units or in SI units. R value of the gas is 287 ideal gas into temperature. So temperature is 40 is given 40 degrees centigrade. I can substitute Kelvin 273. So finally density for a given temperature in Kelvin I can find out it as 1.13 kg per meter. So even though the solution is given here, please all of you find out by calculator also. If any changes are there, please make the changes. So now using this density, one can find out Reynolds number. But characteristic length should be known. So that characteristic length, what is the characteristic length? At what height the flow is taking place, that you can consider it as 5. Okay, 5. Total width, because he's here, it is not the length of the collector, it is the width 1 meters. So even if you consider the width 5 into 1 meters, that becomes the entire cross section area. or section area or characteristic length if you consider always in the Reynolds number characteristic length if you consider always we are taking this height. Okay, so that will be 5 centimeter. So to convert that in meters, we have divided by 100. So 1.13 density into 5 by 100 is 0.05 meters into 4. 4 is velocity. Mu is viscosity. 2.07 into 10 is the viscosity. So by that, Reynolds number is around 10,980. So by the number itself, one can tell it is in turbulent. Because always laminar and turbulent will differentiate by 2000, 4000 values. Okay, 2000 to 4000 it will be transitional flow. But exactly if you see, it is around 2300. 4000 if you take, it will be after transitional flow, it will be attaining the turbulent flow. So it is above 4000 value. So I can tell this as a turbulent flow. Not even in the transitional flows. So here you can see the Nusselt number, the formula is given in the problem. So directly can take the problem equation or else go by this formula. Okay, discussed in the theory. 0.0158 RE rate to 0.8. If not given in the problem, if it is given in the problem itself, Nusselt number is given here. So one for turbulent 0.0196 into RE rate to 0.8. Random number 0.3. This you can consider here. 0.0196 RE rate to 0.8 into random number 0.3. Now we know Reynolds number, random number is given in the problem. And also I have told you, Nusselt number can be written as HL by K or HB by K. Okay, so this B is diameter, but here we don't have diameter, so we are taking characteristic length. So that HL by K, if you see, H is the heat transfer coefficient between air and the plate, that is not given in the problem. Okay, that's not given in the problem, that we need to find out. L is known to us, that we are taking just 0.05. K is the conductivity. So where is that K? K value is given in the problem. Yes, here it is given. K is 0.03 watt per meter Kelvin. K is given. So that K I am substituting here as the denominator 0.03. So H will be heat transfer coefficient between air and the absorber plate, that is around 17.75 watt per meter square into degree centigrade. This is between air and plate. Now using this heat transfer coefficient, as I told you, one can find out the temperature at the outlet. So for that, what they have done here in this problem, they have assumed heat absorbed by the plate is equal to heat gained by the air. But in reality, it is not correct. In reality, some bottom losses will be there. Then again, some top losses will be there. Some side losses will be there. Okay. But in the problem, we have not mentioned any losses. We have not mentioned any insulation materials or conductivity of that insulation material or inside material. So whenever such things are not mentioned in the problem, and they are considering here negligible. So taking this heat absorbed by the plate equal to heat gained by the air or the fluid. So heat gained by the fluid, all of you know that it is mCp delta T. What is delta T? Outlet by inlet temperature, that is the gain in temperature. Gain in temperature difference. Cp of the given fluid. If it is water, go by different value. If it is air, for air they have given the value 1.005. That I can consider. Then M is the mass flow rate of air. So mass flow rate of air is not mentioned in the problem, but indirectly we may find out. Now see this importance. S is total heat transfer falling on of the heat falling on the collector by the solar radiation, that is 630 watt per meter square. Okay. Now if I multiply this tau alpha, as we discussed in the liquid factor collector, that will be the total heat flux or the effective heat flux falling on the absorber plate after the glass cover. So we are going to multiply this tau alpha, that is given in the problem. Then into area of the surface. Okay. So what is the surface area of the plate? Surface area of the plate is width into length. Okay, so that width into length is 1 into 3 meters. But before that, we need to consider here mass flow rate of air. Now, how to consider the mass flow rate of air? Mass flow rate of any fluid is given by rho AV. If you recall that rho AV is nothing but the mass flow rate of the air. Or A1 V1 equal to A2 V2 also you know continuity equation. And in that condition, we have been taken for inlet and outlet both sides. So rho can be cancelled. But here for only outlet side or the inlet side, if you consider the mass flow rate, it is going to remain same. So as the area and velocity remain same because channel is not changing the area. Okay, so area into V into rho if you consider that becomes the mass flow rate of the given air at the section or any section of the flow. So area is, see the area now. Area is the channel area you have to consider. Height is 5 centimeter. Okay, height is 5 centimeter. So they have converted to 5 meters into length. Sorry, width. Width is 1 meters. This becomes the area. Area of the channel of air. If you see, this is inlet side. What the sketch is shown, it is not from the side view. It is from the side, front or back side view. So 1 meter is the width of channel, 5 centimeter is the height of the airflow channel. So this is flowing perpendicular to the screen. What I am showing here. So 1 into 0.05 meters. That is area. Into velocity is 4 meters per second. Density is 1.13. So from this one can find out mass flow rate of air. Once you found out this, now directly substitute mass flow rate, Cp value given in the problem, Cp value 1.005 degrees. Okay. Then T naught is the outlet temperature. What we need to find out? Here, find out the temperature of air coming out of the solar collector. T naught is unknown. Ti is given in the problem 40 degrees centigrade. S is the solar incident radiation on the collector. After losses, after tau alpha product, how much is received in this bracket into area of the collector. It is 1 into 3. So here area of the collector is different, area of the flow channel is different. That should be taken carefully. Or if in the problem they have not mentioned the differences, directly what you can do 1 by 3 itself is the length of flow. So here 1 into 3 is nothing but the width of the collector. Length of the collector is mentioned as 3 meters in the problem, 3 meters. So we have taken here 1 into 3. So now once you substitute all these known values, the outlet temperature, what you can find out is the outlet temperature of the air. So air has received 6.4 degrees extra once it is coming out. So this is the temperature at the outlet. So one similar problem I have taken for the water heater also. So this you can take it as homework. It's a similar way what you have to solve. Okay. In a similar way, we are solving this water heater also. And some data is given in the problem itself. And some equations are assumed in the solution. So what are the equation for Nusselt number is assumed here can be mentioned in the problem also. Because this Nusselt number is again different what they have used here. This Nusselt number is not as per the book what is given. This is from the data index. So like this, some equations will be mentioned in the problem directly. So using this, you can also find out the outlet temperature of the water. Okay. So I think at this point, we'll stop the class. So from the next class, we'll start with the concentrated collectors.